Molecular polarity. Bond polarity. Atoms with different electronegativities form polar bond. For example, carbon bonded to chlorine. This carbon is less electronegative than chlorine. Chlorine is more electronegative than carbon. The more electronegative atom tend to attract the shared electron towards itself, means two electrons in this bond, the position of two electrons in this bond is closer to the chlorine compared to carbon, because chlorine tend to attract the shared electron towards itself because it is more electronegative. So the chlorine is delta minus, means this region, this chlorine region, is partially negative. The carbon region is partially positive. So when the electronegativity between the two atoms are different, the bond is polar bond. Same goes to C bonded to F. Fluorine is more electronegative than carbon. The fluorine tends to attract two electrons towards itself because it's more electronegative. So the fluorine region is partially negative, delta minus. The carbon region partially positive, delta plus. Different electronegativity between the two atoms that are bonded cause polar bond. If the electronegativity of two atoms which are bonded together are the same, the bond is nonpolar bond. For example, C bonded to C, nonpolar bond. Bromine bonded to bromine, nonpolar bond. The molecular polarity shows net imbalance of a charge. For this one, for example, CH3Cl, this is carbon atom bonded to 3 hydrogen atom, and this is chlorine atom. Chlorine is more electronegative compared to carbon and hydrogen, means the electron, these two electrons in the bonding, will be closer to the chlorine because chlorine is more electronegative, so it tends to attract these two electrons towards itself, causing this region electron-rich region, and the region of the atoms with less electronegative, electron-poor region. Dipole moment, symbol mu, is a quantitative measure of molecular polarity, means the net imbalance of a charge can be measured by dipole moment. So dipole moment, a quantitative measure of molecular polarity. Mu equal to Q times R. Q is charge, the unit of Q is coulomb, C. R is the distance between charges, the unit is meter. So Q times R, coulomb meter, the unit is dBi. 1 dBi equal to 3.36 times 10 to the power of negative 30 coulomb meter. Resultant dipole moment can be determined by molecular shape and bond polarity. For resultant dipole moment, we look at the value of mu. When mu is equal to 0, the molecule is nonpolar molecule. If mu is not equal to 0, the molecule is polar molecule. For two atoms bonded together to form a molecule, for example, I2 only involve two atoms together bonded. So I2, both I have same electronegativity. If they have same electronegativity, the resultant dipole moment is 0. So this is nonpolar molecule. For Cl bonded to I, their electronegativity are different. If the electronegativity between the two atoms are different, means this is polar bond. So this is the molecule. Resultant dipole moment is not equal to 0 and it is polar molecule. For molecule which has more than two atoms and there are different atoms, if you look at carbon dioxide, CO2, the central atom is carbon, and the surrounding atoms are oxygen, and they are the same. Oxygen are surrounding atom. The bond between carbon and oxygen, this bond is polar bond. Carbon and oxygen is polar bond because they have different electronegativity. Carbon and oxygen have different electronegativity. O is more electronegative than carbon, means these electrons are attracted to O more than to carbon. So that's why this arrow shows the electron attracted more to oxygen. That's why this arrow shows to the left or pointed to the left. And same goes to this one, the arrow is pointed to the right because oxygen is more electronegative than carbon. So the position of this electron is more closer to oxygen compared to carbon. Even though carbon and oxygen have different electronegative, so means this is polar bond, but the two bond dipoles cancel each other because this one is pointing to the left, this one pointing to the right, so they cancel each other, means the resultant dipole moment will equal to 0. Even though carbon and oxygen have polar bond, this carbon dioxide is non-polar molecule. For this one, COS, the carbon and oxygen, polar bond because they have different electronegativity. Carbon and sulfur, polar bond, they have different electronegativity, but the difference in electronegativity value are different. This one between C and O, it has different value. C and S, different value. So that's why the whole molecule is polar molecule because they cannot cancel out each other because the value between CO is different than value between CS. The CO and CS bond are polar and the two bond dipoles do not cancel each other because they have different value. Electronegativity CO is different for electronegativity value CS. For this one, they are the same, CO and CO. That's why they can cancel each other. But this one, they cannot cancel each other because if you look at the position of C and O is further than the position of C and S in periodic table. That's why the arrow is shorter. So the length of the arrow show the position of carbon and S in the periodic table. If carbon is closer to S compared to carbon and O, the length of the arrow is shorter than this length of the arrow. So this molecule resultant dipole moment is not equal to 0 and this molecule is polar molecule. Next, CCl4. Carbon and chlorine form polar bond. This is polar bond because the electronegativity between carbon and chlorine are different. Chlorine is more electronegative than carbon. So all Cl bond are polar bond, but all four bond dipole cancel each other because the value of Cl the same, C and L is the same, C and L is the same, C and L is the same. So all values C and L are the same, causing resultant dipole moment equal to 0. They can cancel each other. So this CCl4 is non-polar molecule. Next, BF2Br. The B central atom bond to F fluorine atom. This bond is polar bond because they have different electronegativity. F and B different electronegativity. This is also polar bond, and B bonded to Br is also polar bond because they have different electronegativity. The value of B and F electronegativity difference value of B and F and B and Br are different. So This is polar molecule. The BF and BR bond are polar, and the 3 bond dipoles do not cancel each other because electronegativity difference value B and F, B and BR are different. The electronegativity difference of B and F here and B and F here are the same because it's BF, so their electronegativity difference are the same. But the electronegativity difference between B and BR is different from these two, causing the 3 bonds dipoles do not cancel each other. Resultant dipole moment is not equal to 0. This molecule is polar molecule. A molecule will be nonpolar if the bonds are nonpolar. For example, this one. This bond is nonpolar, so this molecule is nonpolar molecule. Or no lone pair in central atom, all surrounding atoms are the same. This is central atom, all surrounding atom are the same, and the central atom has no lone pair. Means this is nonpolar molecule. For this one, carbon, the surrounding atoms are the same and the central atom has no lone pair electron. So this is nonpolar molecule. A molecule will be polar if the central atom of the molecule has lone pair, even though the surrounding atoms are the same. This nitrogen has same surrounding atom, H. All surrounding atoms are the same, but the central atom has one lone pair. If the molecule has same surrounding atom but has lone pair electron, the molecule will be polar molecule. Same goes to water, same surrounding atom but it has the lone pair electron, so this is polar molecule. For this one, polar molecule because the central atom has lone pair electron. This is polar molecule because the central atom has lone pair electron. More exception. However, molecule with lone pair can also be nonpolar if you look at the molecular shape for this one, this central atom has same surrounding atom, but it has lone pair electron. If the molecule has same surrounding atom but have lone pair, it will be polar. But the exception is the lone pair. If you look at the lone pair, all the lone pair are the planes are on the plane. This surrounding atom is on top of A. This surrounding atom is below A. All the lone pair are on the plane. So all these lone pair, they can cancel out each other because they are on the same plane. So this one can cancel out each other, and this atom surrounding atom can cancel out each other with this surrounding atom, causing this molecule as nonpolar molecule because the resultant dipole moment is equal to 0 because they can cancel out each other. Same goes to this one. Even though it has same surrounding atoms and it has lone pair electron, if the molecule has lone pair electron, usually it is polar molecule. But for this one, it's non-polar molecule because if you look at the lone pair is on top and below. All the surrounding atom is on the plane. Means this lone pair, two lone pair can cancel out each other because one on top, one below. And all the surrounding atom is on the plane. All the surrounding atom can cancel out each other on the plane. And the lone pair on top and lone pair below can cancel out each other. So this is the exception. So these two are non-polar molecule. Always look at the molecular shape as well to know the resultant dipole moment value, whether it's equal to 0 or not equal to 0. If it's not equal to 0, it's polar molecule. If it is equal to 0, it's non-polar molecule.